The launch of NASA's Voyager probes marked the initiation of a momentous journey beyond our solar system, underscoring our ability to observe not only Earth, but also the celestial expanse. Even after 45 years, these remarkable spacecraft continue to furnish scientists with updated insights into the cosmos. Despite having a memory capacity 3 million times smaller than a typical smartphone and operating 38,000 times slower than a 5G internet connection, these extraordinary probes remain at the forefront of space exploration. However, in a surprising turn of events, the Voyagers have encountered an astounding discovery. What are their current activities? What do the Voyager spacecraft have in store for them? On September 5, 1977, Voyager 1 commenced its remarkable journey from Cape Canaveral, Florida, propelled by the Titan IIIA Centaur rocket. Merely 15 days later, on August 20, 1977, Voyager 2 followed suit, embarking on a twin odyssey into the cosmos. Initially tasked with exploring the gas giants of our solar system, Jupiter and Saturn, and their attendant moons, these intrepid explorers exceeded their initial objectives, journeying to the outermost reaches of our celestial neighborhood. Voyager 1 and Voyager 2 have established numerous records during their epic odyssey. They have outlasted any other spacecraft in history, traveling farther from Earth than any other human-made objects. In fact, they have ventured into interstellar space, making them the first human creations to do so. Their journey into interstellar space, beyond the sun's sphere of influence and into uncharted galactic territory, has provided scientists with invaluable data. Situated over 12 billion miles from Earth, these pioneering interstellar probes continue to astound physicists with their findings. The recent astonishing discovery is one such revelation that scientists could not have foreseen. The achievements of the Voyager twin probes have been nothing short of spectacular. Their early observations of Jupiter and Saturn's moons made more than 4 decades ago astonished researchers and shattered previous assumptions about these distant worlds. These moons, once presumed to be as inactive and heavily cratered as our own moon, were found to be brimming with geological activity. Voyager 2, in particular, achieved several significant milestones during its journey. It became the first spacecraft to fly by Uranus in 1986, and just 3 years later, conducted a flyby of Neptune. To this day, it remains the sole spacecraft to have ventured on such a path. As the spacecraft continue their remarkable journey, NASA has implemented measures to extend their operational lifespans. Over the past 3 years, non-essential components and heaters have been deactivated to conserve energy, allowing them to operate well into the next decade, with an estimated mission end date of 2030. The Voyager missions represent a bittersweet culmination for the dedicated scientists and engineers who have been part of this extraordinary voyage from its inception. Their unwavering commitment and hard work have ensured the project's continued success. The data returned by the Voyagers has yielded valuable insights, driven numerous scientific discoveries, and inspired generations of researchers and space enthusiasts. Voyager 1 and Voyager 2 are not merely ordinary spacecraft. They were meticulously engineered to serve as stable platforms, with a rotation rate more than 15 times slower than the hour hand of a clock. This design minimized visual blur as the spacecraft captured images and data while hurtling through space. Their impressive imaging capabilities began to astound scientists and the public even before their encounters with the outer planets. The spacecraft initiated the transmission of images of Jupiter while still several months away from the planet. These early images, unveiling Jupiter's swirling clouds and iconic Great Red Spot, captivated audiences at NASA's Jet Propulsion Laboratory. Nevertheless, the discovery of active volcanoes on Jupiter's moon, Io, was the most remarkable development that set the stage for the Voyager's groundbreaking observations. Io, slightly larger than Earth's moon, turned out to be the most volcanically active body in the solar system. The spacecraft's instruments detected peculiar signals from Io, which were corroborated by the vivid images they captured. These images unveiled towering volcanic plumes and a surface marked by the ejection of volcanic material. One of Io's most prominent volcanoes, Pele, has erupted to heights 30 times greater than Mount Everest, covering an area almost the size of France. The Voyager spacecraft amassed over 33,000 images of Jupiter and its moons, showcasing the planet's splendor and the extraordinary diversity of lunar landscapes in the Jovian system. Prior to the recent astounding discovery, the twin Voyagers have been making breathtaking discoveries since their launch. One of the most astonishing findings was the revelation of Jupiter's rings. While faint, these rings were a revelation, and added to the intrigue of the gas giant. Furthermore, Voyager 2 revealed that Europa, one of Jupiter's 53 named moons, harbored an icy shell believed to be over 60 miles thick. These findings challenged earlier assumptions about the nature of these distant celestial bodies and prompted further investigations into the potential habitability of icy moons. As the Voyagers departed from Jupiter, they received a gravity assist that propelled them toward Saturn. Without this crucial boost, they would have been unable to escape the Sun's gravitational pull and venture deeper into space. Voyager 1 and Voyager 2 soon embarked on separate paths, each heading toward new frontiers. Voyager 1's trajectory took it near Saturn's moon Titan, shrouded in an orange, hazy atmosphere. The mysteries of this moon piqued scientists' interest, leading to further studies of its complex chemistry. Voyager 1 then veered northward, departing from the plane of the planets, and began its journey beyond the realm of our solar system. In contrast, Voyager 2 embarked on a series of adventures that brought it to the outermost planets of the solar system. In 1986, it executed a historic flyby of Uranus, where it discovered 10 previously unknown moons, increasing the planet's moon count. 3 years later, Voyager 2 reached Neptune, revealing the remarkable features of this distant ice giant. During its encounter with Neptune, Voyager 2 recorded wind speeds of up to 1,000 miles per hour, making it the fastest wind ever recorded on a planet in our solar system. As the spacecraft passed within 2,180 miles of Neptune's azure methane-rich atmosphere, it provided unprecedented insights into this distant world. Triton, Neptune's largest moon, was found to be one of the coldest places in the solar system, with surface temperatures plummeting to -391 degrees Fahrenheit, -235 degrees Celsius. Triton also exhibited unique features, including ice volcanoes that ejected nitrogen gas and icy particles 5 miles into its thin atmosphere. These discoveries expanded our understanding of the variety and complexity of celestial bodies in our solar system, even in the outermost regions. One individual who played a pivotal role in extending the missions beyond their initial goals was the renowned astronomer Carl Sagan. As a member of the Voyager mission's imaging team, he passionately advocated for capturing one last set of images before the cameras on both spacecraft were turned off. These images would offer a parting gift to humanity, a final glimpse of our home planet from the distant depths of space. Sagan's persistence paid off. On Valentine's Day in 1990, Voyager 1 turned its camera back toward the inner solar system and captured a series of 60 images. The most iconic among them, known as the pale blue dot, remains an unforgettable symbol of our place in the cosmos. Taken from a distance of 3.8 billion miles, it is the farthest image of our planet ever recorded. Earth appears as a tiny pale blue speck, barely distinguishable in the vastness of space. The Voyager mission is an astonishing tale of durability and longevity that reads like a space-age superhero comic. Even after more than 40 years, these spacecraft continue to operate, sending us valuable data from the farthest reaches of our cosmic neighborhood. Now, let's delve into an interesting aspect of these missions, their use of an archaic 8-track tape system. Yes, you heard that right. 8-track tapes were all the rage in the 70s, and the Voyager probes still use them. It's a testament to the genius of the mission's designers that these trusty tapes have endured the test of time. But why 8-track tapes, you ask? In the early days of space exploration, digital storage as we know it today was still in its infancy. So, they needed a reliable and durable data storage system, and those 8-track tapes fit the bill. They have proven to be like the indestructible workhorses of the cosmic age. What's even more incredible is that the data on these tapes isn't just your run-of-the-mill tunes. It's precious scientific data, about the outer planets, moons, and interstellar space. These tapes hold the key to understanding some of the most profound mysteries of the universe. Despite being exposed to extreme temperatures, cosmic radiation, and the vacuum of space, these aging explorers keep on going. It's like sending your grandparents on a trek through Antarctica, and they not only survive, but thrive. So, what strategies ensured the success of the Voyager missions? One crucial technique was the use of gravity assist maneuvers, which played a pivotal role in these legendary interstellar missions. Imagine two brave spacecraft, Voyager 1 and Voyager 2, embarking on their audacious quest to explore the outer reaches of our solar system. To reach these distant destinations and gather invaluable data, they needed a boost beyond what their own propulsion systems could provide. This is where gravity assists come into play, akin to cosmic choreography. Instead of relying solely on their engines, these spacecraft engaged in a celestial dance with some of our solar system's massive planets, utilizing their immense gravitational pull to slingshot themselves on their way. This ingenious maneuver allowed them to conserve precious fuel and gain the velocity needed to visit multiple destinations on their grand tour. Gravity assist, also known as a gravitational slingshot, involves transferring some of a planet's momentum to the spacecraft as it passes by. For example, Voyager 1 approached Jupiter, a massive gas giant with a gravitational pull to match. With precision that could only be achieved by the brightest minds at NASA's Jet Propulsion Laboratory, Voyager 1 swung by Jupiter at just the right angle and speed. Jupiter's gravity accelerated the spacecraft to a higher velocity, giving it a cosmic boost. However, the precision required for this maneuver was mind-boggling. If Voyager 1 had approached Jupiter at the wrong angle or speed, it could have sent the spacecraft off course. But the scientists and engineers behind this cosmic ballet got it right. Not just once, but multiple times. These gravity assists propelled Voyager 1 and Voyager 2 on a breathtaking journey through the solar system. Voyager 2, for instance, used gravity assists from Jupiter and Saturn to reach Uranus and Neptune. These celestial dances were crucial in making the grand tour possible. The concept behind gravity assists is simple, but the execution is breathtakingly complex. Voyager 2's grand tour required an incredible degree of precision. Missing any of these slingshots could have spelled mission failure. Nevertheless, the people behind these missions were determined and relentless in their pursuit of knowledge. Although the Voyager missions made use of gravity assist maneuvers to navigate the cosmos, another critical component ensured their success: the Deep Space Network, DSN. The DSN is a network of massive radio antennas strategically located in various corners of the world, including California, Spain, and Australia. These colossal dishes, ranging from 26 meters to a whopping 70 meters in diameter, function as cosmic megaphones, allowing us to communicate with spacecraft traveling beyond our planet. The DSN played a vital role in the Voyager missions. It served as the interstellar telephone line that kept us connected with our intrepid Voyager probes as they journeyed into the great unknown. The DSN doesn't just receive signals, it also sends commands. Missions like Voyager are dynamic, requiring adjustments, tweaks, and redirects. Scientists and engineers sent these commands via the DSN, which transmitted them into space to reach Voyager. It facilitated a two-way conversation between Earth and the farthest human-made objects in the cosmos. The remarkable thing about the DSN is that it operates around the clock, tirelessly listening for signals from the distant probes. It's like having an unblinking eye on the cosmos, ensuring that we stay connected with our spacecraft, even when they're billions of miles away. The Voyager missions are a testament to the power of collaboration and innovation. While the spacecraft embarked on their incredible journeys, the DSN ensured they were never truly alone. It bridged the gap between our planet and the unknown, allowing us to explore the outer planets and venture into interstellar space. In essence, the Deep Space Network isn't just a collection of antennas, it's our lifeline to the cosmos. It ensures that the stories of the Voyager missions continue to be written, even as the spacecraft journey beyond our solar system into the uncharted territory of interstellar space. So, what is the heliopause, and what fascinating discovery did Voyager 2 find there? The heliopause is the boundary that separates our sun's influence from the vast interstellar space beyond. The exact location of this boundary was initially uncertain, with various estimates and theories. Early estimations placed it as close as Jupiter, but subsequent calculations refined our understanding. In 1993, astronomer Bill Gurney's projections placed the heliopause between 168 and 177 astronomical units, AU. To put this into perspective, 1 AU is roughly 93 million miles, the distance between the Earth and the Sun. Gurney's projections turned out to be remarkably accurate, as Voyager 1 reached the heliopause about 20 years later and detected the expected rise in plasma density. However, this posed a puzzling question. When Voyager 1 reached the heliopause, it observed an increase in plasma density, but no significant shift in the ambient magnetic field direction. This was unexpected because if the spacecraft had traveled from a region where the magnetic field originated from the Sun to one where it came from other stars, a noticeable change should have occurred. Voyager 2 added to the mystery when it reached the heliopause at the same distance as its twin, 120 AU from Earth, but also failed to detect any magnetic field changes. Theoretical models predicting the behavior of the heliosphere and its interaction with the interstellar environment faced challenges due to these unexpected observations. The heliosphere was expected to fluctuate in sync with the Sun's 11-year cycle, but this did not align with the data gathered by the Voyagers. The solar wind, which ebbs and flows with the Sun's cycle, was at its strongest when Voyager 2 arrived at the heliopause. The heliopause should have been further out than 120 AU, adding another layer of complexity. Nevertheless, the Voyager's data have provided valuable insights for refining theoretical models. Scientists now believe that our Sun has transitioned from a hot, ionized zone to a partially ionized section of our galaxy. This transition was likely triggered by nearby supernovae, ancient stars that exploded at the end of their lives, heating the surrounding area while removing electrons from adjacent atoms. As ageless explorers, Voyager 1 and Voyager 2 continue their solitary journeys through interstellar space, leaving behind the planets and moons they once called home. But what lies ahead for these indefatigable travelers? It's a cosmic guessing game, but there are some possibilities to consider. These probes are now headed in different directions, with Voyager 1 racing toward the constellation Ophiuchus, while Voyager 2 is making its way toward the constellation Cetus. Some scientists predict that they will likely outlast our species, enduring for millions of years. One day, they might encounter other star systems, bringing with them a message from a long-lost Earth. Imagine an alien civilization stumbling upon these ancient artifacts of human ingenuity, carrying the golden record, a time capsule of our existence. Who knows what mysteries they might uncover? The Voyager missions represent a testament to human ingenuity, persistence, and our unquenchable curiosity about the cosmos. They continue to inspire and remind us of the vastness of space and the boundless potential of exploration.